Could be E2, one reflection, or it could be the dihedral group of order 4, which is the same as the Klein 4 group. That's it. Those are the only possibilities for gamma bar. Particularly has order less than or equal to 4. And the proof is easy. Take the line generated by A. So here's A, here's 2A, here's minus A, minus 2A, etc. 0. Now, this subgroup has to be preserved by gamma bar. So if I have a gamma in gamma bar, and I apply gamma to A, what is the possibility for gamma of A? Well, it has to be an element of this subgroup. That's the first thing. So some multiple of A. And the second thing is, it has to have the same distance from the origin as A, because gamma is an element in the orthogonal group, right, which preserves distance. Now, there are only two things of the same distance from the origin from A here, and those are A and minus A. So this has to be plus or minus A, as in CA and same length. Okay, well that just about does it. Because if it were a rotation, if gamma is in SO2, then either gamma is the identity element or gamma is minus the identity element. So the only rotations in the group have order 1 or 2. Because if you have a rotation, you know where you take this element, that tells you the angle of rotation. It's either 0 or pi. And once I know what rotations are in the group, that restricts what so that says the only cyclic groups I could have are this. The only possible dihedral groups I could have is this. So if I had a bigger dihedral group, I'd have a rotation at a different angle. And in fact, you can get these dihedral groups because we can also take A to minus A by taking the reflection around this perpendicular line. Right? And that commutes with the rotation through 180 degrees. So the group could be either just nothing. It could be the rotation, that would be C2. It could be the reflection around this line, which would be the group E2, or it could be the Klein 4 group where you both rotate and reflect. Those are the only possibilities to take A to minus A. Okay? So once I know that the lattice is of this form, the subgroup is very seriously restricted. And finally, last time, we showed that if L is equal to ZA plus DB, then the only possibilities for gamma bar are Cn, 2n, where n is equal to 1, 2, 3, 4, or 6. So again, the largest group we could have would have order 12. If we have the largest group we can have is of order 4. And I gave you one proof of that based on the quadratic polynomial satisfied by, my proof last time was saying if gamma is in gamma bar is a rotation. So again, to prove these things, you only have to show that the only rotations in gamma have order 1, 2, 3, 4, 6. Because if I had a different dihedral group, it would have rotations of order n in it. Right? E2n has a rotation of order n. So if I have a rotation, I just have to classify that. And I look at the characteristic polynomial of gamma. It looks like x squared, well, I'll write it like this. This will make it even more obvious. 2 cosine of theta x plus 1. So there's the characteristic polynomial where theta is the angle of rotation. So this number, whatever it is an absolute value less than or equal to 2. Right? Because cosine theta is an absolute value less than or equal to 1. So the absolute value of 2 cosine theta is less than or equal to 2. On the other hand, since gamma preserves this lattice, then we can write down the matrix of gamma with respect to the bases A and B of this lattice, and the 2 by 2 matrix of gamma has to be the integers. But the matrix A of gamma with respect to the basis AB is integral. Doesn't just have real entries, it has integer entries, because it takes A to an integer multiple of A plus an integer multiple of B, and B to, right? Therefore, its trace is an integer. So, integral So therefore, whatever this angle is, 2 cosine theta is some number between -2 and 2, which is an integer. There are only 5 integers between -2 and 2. -2, -1, 0, 1, and 2. And once I know what 2 cosine theta is, 2 cosine theta is equal to -2, -1, 0, 1, or 2. And that tells me what cosine theta is. It's -1, -1/2, 0, 1/2, or 1. Once I know that, I know what the angle is. And you find exactly these 5 angles. So that's the proof that you can only get those. Now you might want to know, when do you get one group, when do you get the other? So that's how I'm going to finish today, with a little bit of hand waving. And then if you want to, you can finish reading all about the wallpaper patterns in art. And I'm going to hold off on that because when you take the course in chemistry, you'll do all those wallpaper patterns. And you'll also do the case of the 3 dimensions, which is even more interesting. So if you have a general, what is the classification of lattices L in part 2? Well, the classification, I mean, you might just ask for all subgroups of R2, but if you're trying to figure out what groups can act on them to determine what gamma bar can be, what automorphisms you can have. If I change L and I act on R2 by an element in the orthogonal group, that doesn't change the possibilities for gamma bar. You just conjugate gamma bar by an element. So changing L to gamma L with gamma in O2 just conjugates gamma bar, the automorphism of L by gamma. So you get a similar subgroup of O2, similar finite subgroup of O2. So if you change by an element to orthogonal group, and also changing L to a multiple of L, let's say a C times L, where C is in R star, doesn't change gamma. And if you just take everything, if you have a lattice AB, here's A and B, and you scale A and B out by the same fixed scalar, CA, CB, then anytime you had a rotation that preserved L, we would preserve this, because rotations commute with multiplication by scaling matrices. So this just means take everything in L and scale it out. So I really want to just classify lattices up to the action on the space of lattices by elements in the orthogonal group and scalars. So I'll tell you all lattices up to the elements in the orthogonal group and scalars. It's a famous mathematical picture. And then for each lattice, I'll tell you what the possibilities are for gamma bar. That'll be the end of this. So L up to action of O2 and R star on. Well, we know that the lattice has a shortest vector, right? Because you can't get vectors in the lattice arbitrarily close to the origin. The distance in a lattice of vectors is bounded away from each other. Okay, use my action of scaling on the lattice to make the shortest vector have length 1, right? That I can do. So scale, so the shortest vector R star, the scale, so shortest vector has length 1. And then I really only need positive reals for that. Because you only have to scale by positive reals to get length 1. And then use SO2 to rotate A so that it doesn't just have length 1, it's actually equal to the vector 1. So by scaling my lattice and by rotating my shortest vector, I can assume that the shortest vector of the lattice is actually the number 1. Okay, everyone agree? The first thing I do is I scale to get the shortest vector on this circle, and then I have a unique, look, that wasn't a very good circle. then I have a unique rotation so that the shortest vector has length 1. I still have a reflection left, and I still have a negative left to work with. Okay? Now, where is the second vector on this lattice? Well, first of all, the second vector has to be outside of this circle. That's the vector b. The first thing we know is the absolute value of b has to be at least 1. Okay? And so it lies outside this circle. And we can also replace b by minus b. Which gives the same subgroup, ZA plus DB is the same thing, to make sure that its imaginary part is positive. We know its imaginary part is non-zero. I'm sorry, its second coordinate, the y coordinate, is non-zero. Because if the y coordinate was 0, it would be linearly dependent with a. But we know a and b are linearly independent. So whatever b is, it's either above here or it's below here, but it's not on this line. So by replacing it by minus b, we can assume that the y coordinate is positive. So it's outside of this circle up here, somewhere. And finally, we get the same subgroup. So this doesn't affect, we're really interested in what this subgroup is. We can also replace b by any multiple of a, and we'll still get the same subgroup. So replace b by a multiple of a to shift it back so that its x coordinate lies between a half and minus a half. X coordinate is between a half and minus a half. This is just a convention. We could make it between 0 and 1. Or we could make it between 3 and 4. We can get it in any interval of length 1, right, by shifting by multiples of a. So I make it between a half and minus a half, which puts me in the following region. It's the line coming down at minus a half, then outside the circle, and then a line going up and a half, like that. Okay, so b is somewhere in this region and gives us the same lattice that we're interested in, up to these rotations. And now we still have a reflection that we could use, so we could still reflect the lattice around this line, and that would take a to minus a, which we could replace it to, and it would take b to the other thing in this, on the other side of this region. So really, the classification of lattices is in this half of this region. So the b's that lie in this half of the region classify the lattices that are possible up to the action of the orthogonal group and scaling. So this would be reflection in B, and if we reflected in A, took the same reflection in A, we get minus A, which we could replace by A equal 1. But this would look like it, the same lattice. So the classification of lattices is really just the points in this bizarre region of space. So L is isomorphic or to L of B, or B in the marked region. Where L of B is Z plus ZB, because we're using the vector A is equal to 1. And, yes?
How do you know that when you add or subtract multiples of A to get B's x coordinate between a and a half, that B still has an equal greater than or equal to 1?
Ah, very good. Then you have to translate it back up. Very good point. Namely, I could have started out here, and then I could have translated it back into here, and then I'd have to replace it by the vector on the other side of it. You're absolutely right. There's a subtle point that in the translation of such elements, you might end up inside of the circle, in which case you'd have to replace the lattice by the lattice where you scaled again and took that vector to 1 and saw where the vector A went. But I'm asking you to believe that this process eventually lands you in this region. It's not completely obvious. Thank you. That was the subtle thing I was trying to line over. Yes?
Why is that a problem if A is the shortest vector of the lattice?
Because in the translation, you might have gotten to a shorter vector.
But
Very good point. Very good point. Namely, if we started with a vector in this region, yeah, I think that's the answer to your question. Thank you. I'm fudging it. Namely, we cannot, by any translation, none of these vectors are legally inside the circle because our assumption was that we had already set the lattice up so that A was the shortest vector. Therefore, no matter what vector we replace B by, it still has to have absolute value bigger than 1. So that if we had started off with a lattice out here, there would have been a shorter vector than A in it. Namely, the translation of this back over here. And we would have been with the incorrect vector A. Thank you.
But then by the same reasoning, your statement that L is isomorphic to your little region,
Yes.
then for you can certainly choose a B in your region such that you get a problem.
A B in this region, I have a problem? How? All these B are length longer than A. And any translate of them has length longer than A. By A.
Are you considering B like a rotation?
No. B is the second lattice
Oh,
vector.
okay.
So the lattice would be generated by 1 and B. And I claim that those lattices are inequivalent under the orthogonal group and cannot be scaled 1 into another.
Okay.
Now, there are two very special points of this region. That's what I want to show you. Namely, this point here and this point here. They're sort of boundary points in the region. And if you take B to be this point here, then you get a very famous lattice that looks like this. You have 1, and you have an angle of 60 degrees, which you'll figure out that that angle is 60 degrees where that thing meets. And then you have these vectors, and there are 6 vectors around the origin that have the same length as A. 6 vectors around the origin. This is the famous hexagonal lattice. If you use this lattice to pack spheres by putting a sphere putting a circle at each lattice point of radius 1/2 so that the spheres just touch each other like this, you get the best packing of two-dimensional space that you can arrange with spheres. It covers the most of two-dimensional space. I'm throwing it behind me, but and there are 6 spheres. 7. That should be 6. Did I put 7 lines here? Yeah. That was my problem. Thank you. There are 6. You know what the problem? There are 6 spheres around the origin sphere, and it covers about 75% of space with circles. And this is the most efficient way to put spheres in a regular way into 2 space, and it's the way that was discovered by the bees long before we were born. So, I mean, if you had to make a honeycomb, and you wanted to make circular objects, and you wanted not to waste any space in your hive, this is what you would do. Okay? The lattice that has basis vector here is the famous rectangular lattice, so there are 4 vectors of length 1, and they're orthogonal to each other. And that's the packing of space that, where you have just integer values X and Y. That's a nice packing, but it's not as efficient as the hexagonal packing. And the packings and the lattices that correspond to vectors along this little border line are the lattices where you have more than 2 vectors of the same length, but not in nice angles like this. Here's a 90-degree angle, here's a 60-degree angle. Now, the general lattice is, if B is inside of this, then the only possibility for gamma bar is like we did in the if B is inside of region. Actually inside, namely not on this boundary point, not on this boundary circle, not on this boundary point, then only possibility for gamma bar is equal to 1 or C2. I think that's what I'm going to say. Yes, correct. And C2 just means minus the identity map. Minus the identity map preserves any lattice because it takes A to minus A and B to minus B. But there are no rotations that preserve the map because any rotation would have to take A to a vector of the same length as A. And so this group is really the group I should have called, sorry. The only vector of the same length as A is minus A. And the reflection doesn't work because it takes B out of this region, so it's C2. if B is orthogonal to A, so your lattice looks like this, so that would be a vector along this line, then you can get gamma bar equal to 1, C2, but you can also have the reflection around this line would take B to minus B, and likewise the reflection around that line would take A to minus A. So you can also have the group D4, which contains those two reflections, the two orthogonal reflections. Okay? Or it could be a subgroup of D4, it could be one of the reflections and not have that rotation in it, so it could be D2 or D4. And the only lattices that have extra rotations in them are these two lattices. So this lattice, we can have gamma bar equal to 1, C2, and there's also a rotation of order 4, C4, and it could also be D4 or D8. And this lattice, the hexagonal lattice, you can have gamma bar equal to 1, a rotation of order 3, C3, C6, a rotation of order 6, takes this vector to that vector, or you can have D6 or D12. And these are the only two lattices which you can get a large group gamma bar for.
Oh, there's C2.
Oh yeah, of course, C2. Yeah, I'm sorry, C2. Yeah, of course, you can always rotate the thing. That's minus one, that's in any lattice, and likewise. But not D4, because you haven't got an orthogonal.
Oh.
Okay? So these are the possibilities for gamma bar for the hexagonal lattice. These are the possibilities for gamma bar for the square lattice. These are the possibilities for gamma bar if you have orthogonal vectors. And here's the possibilities for the general lattice. Then you have to say, okay, if I have L and I have gamma bar, what can I say about gamma? That's an argument that's treated in R. I'm going to do that. Yeah.
So like another way to see is that you only have extra rotations in those two pieces.
Exactly right. Exactly right.
The only two angles and divide two sides.
Exactly. Namely, we proved that if we had a rotation in the lattice, it can have order 2, 3, 4, or 6. Okay? Here we have rotations of order 2. That's easy. That exists for any lattice. Just takes a vector to minus the vector. But if we had a rotation of order 3, we'd have to have this vector in the lattice, right? Given the fact that we had the vector 1. If we had this vector in the lattice and you add 1 to it, you get this vector in the lattice. So we're already in the hexagonal lattice case if we have a rotation of order 3. Likewise, if we have a rotation of order 6. And if we have a rotation of order 4, and we have 1 in the lattice, we have to have this vector as a lattice. Okay? When I write 1, I should be writing 1, 0. I keep writing 1 because I'm thinking of this plane as the complex plane. It's best to think of all this really, and you get to this when you do complex analysis, it's best to think of this as a subregion of a complex plane. And I'm sorry, I keep writing 1, and I think of this as I, and I think of this as a third root of unity. Which is a sixth root, which it is. And this is the element of trace. 2 times the cosine theta is 1, and here times the cosine theta is 0, here the 2 times the cosine theta is minus 1, and here 2 times the cosine theta is minus 2. Okay, so this is a combination of our classification of lattices theorem and our description of what the order of a possible rotation could be. Okay. I back off of this, but I promise you as you guys go on and you study, it turns out that this region is central to the study of number theory. And what we'd really like to know is what that region is for lattices in Rn. And we know it for all the way up to about 8 dimensions, and then it's just vast ignorance. So we would very much like to have a classification of all the lattices, ZA1 plus ZAN, inside of Rn, up to scaling and ON. That's one of the most central objects in modern mathematics. And we know this for n less than or equal to 8. We know what this region looks like, what its topology looks like, everything. And past that, it's the, I would say, the main open question in number theory. So you should at least be exposed to it in R2. This is related to work on sphere packing, and many of you may know that Professor Elkes in the department made a big breakthrough about 5 years ago on constructing very dense sphere packings of high dimensional space. As I said, the hexagonal packing is the best packing known in two-dimensional space. It's going to be proved pretty soon that we know the best packing is in up to 8 dimensions, and in 24-dimensional space we know the best packing of spheres. And the other spaces we don't know how to pack spheres, and since we don't know the dimension of the universe, this would be a good thing to work out in all dimensions, just in case. Even in 3 dimensions, it was only recently proved that the packing of spheres that you see on any New England common, where they stack cannonballs, by first taking the hexagonal packing in one layer, and then stacking balls on the holes in that layer, and then stacking balls on the holes in that layer. So that's also the way you'll find oranges stacked at Haymarket. That's the best packing of spheres in 3 space. So that's been known since the 15th century, but no one proved it mathematically. And there's a horrible proof out there now, which I'm very unhappy with, but it's a proof which uses the computer to analyze thousands and thousands of possible cases. Turns it into a linear programming problem, and it will be extremely nice if one found a nice proof of the fact that physicists and chemists have known for many, many years that this is the best way to pack spheres in 3 space. Anyhow, Professor Elkes has got this great method where he'll determine the best packing of spheres in 8 and 24-dimensional space, those are particularly nice dimensions. Okay, now let me go on with a little bit of language because it's something we can use it all the time. We've been studying the action of the group G, which is R2.O2 of motions on R2. Now R2 is just a set of points. And we might want to study group actions on a set. That's the general group G acting actions on a general set S. And develop some language for it because it comes up all the time in mathematics. So a group action on a set is a mapping from G cross S into S. If you have an element if you have a pair, G and S, it maps it to what the element of the group does to the element in the set. And it has 2 basic properties. The identity is the identity map of the set. So E of S is equal to S for all S. And it's associated. If you take GH and you apply it to S, that's G of what you got by applying H to S. So when you look at this group of motions on R2, this takes a vector S, goes to the vector AS plus B, where you have the element B, A of S. Is AS plus B in this case. But we could take different sets here. We could also take the action, of G on the set of lines L in R2. Because if you act on the points of R2 by the group of motions, it preserves lines. This action preserves the points on the line. Takes it to another line. Or we could take the action of G on the set of triangles. In R2. Because if you have a triangle, and you take the image of A and the image of B and the image of C, those are 3 points. This line is taken to the line through it, the image of A and AB, so it goes to another triangle. And in this case, the different images of this are all triangles congruent to that in the plane, because remember, G preserves distance. So by the Euclidean theorem that the distance of the lengths of the sides of the triangle, determine the congruence class of the triangle, you'd be going to a congruent triangle. Okay? Now, here's some terminology. We call, if S is in S, we define 2 sets. One is a subset of S, called the orbit. And the other is a subgroup of G, called a stabilizer of S. So OS are all the points that G takes S to. So this is the set of S prime equal G of S. Some G and G. And the stabilizer is the subgroup that fixes S. So those things are used all the time for a group action. They're the 2 most important things to do. For each point, you get the orbit and you get the stabilizer. Now let's take a look at some orbits and stabilizers. if we take the normal action of this group on the plane, what is the orbit of 0? What points can you take to 0? Everything. The orbit of 0 here is R2. Because I can find an element that translates, if I want to get 0 to B, I just use translation by B. And what's the stabilizer of 0? That's the group O2. Those are the linear transformations that fix 0, because no translation fixes it, but everything in here fixes it. Okay? Now, a very interesting question is if I look at this action and I fix a line through the origin, maybe this line, what's the orbit of that line under the group of motions of the plane? Can anyone see? That's a hard question. Anyone see what the orbit of this line? Well, what would be the orbit under the rotation group? Any line through the origin, right? Because any line through the origin has some fixed angle from the origin, and rotating by that angle, I could go to there. So now if I have the whole group, what would be the orbit? Every line. OL is equal to S, because if I have any line up there, I can translate it to a line through the origin, it has some fixed angle, then I rotate L to that angle. So this is a case where I can take any line to any other line. In this case, I can't take every triangle to every other triangle, because if I had a triangle like this, I couldn't take it into a triangle like that. They're not congruent with each other. So the orbit here happens to be the triangle's congruent to this. I'm not going to prove that. So sometimes the orbit is a subset of S, and sometimes the orbit is all of S. If the orbit is all of S, we call the action transitive. So these are three key terminology points. If you have a point that can be taken to any point, then the action is transitive. So this action is transitive. The action of O2 on points is not transitive because it preserves distance. So if you had just the action of O2 on the plane, you could not take this point, this vector, into this vector because it preserves distance. Okay, so some actions are transitive, some aren't. Let me give you a very general transitive action that you don't need a space for, you don't need anything. If you start with any group, so this is in some sense the model case of a transitive action. Take G to be your group, any group. To take H to be any subgroup of G, any subgroup, and let S be the set of left cosets. That's a perfectly nice set. And the G action is by left translation. It acts on the set by taking a coset to the translated coset. That is, the identity preserves all the cosets and it's associative. I claim this is transitive. You agree? Well, I just have to find one coset that I can take into anything. And if I take the coset H, and I want to take it to the coset AH, I just translate by A. Okay. So I can get from H to any other coset via this group action. So the orbit of H is equal to S. Okay, what is the stabilizer in this case? The set of elements in G that fixes the coset H. So this is the set of elements G, such that GH is equal to H. What's that?
H.
You got it. So, that if I want to make a transitive action internally from the group, I take any subgroup I want. It doesn't have to be normal, far from it. I take the set to be the set of all cosets. I take the action to be left transitive, left translation. This is transitive, and the stabilizer recovers my subgroup. Okay. What is the stabilizer of another coset? Well, it's the set of G such that GAH is equal to AH. So I claim that this is AHA inverse. Right? I mean, if you work out this identity, just say, that you'll find it. But also, it's easy to see that if you take a G in this form and you multiply it by AH, right? AH, A inverse, times the coset AH is equal to AH, but these two things cancel. HH cancels, so this is just AH. Conversely, anything of that form you can show us in this one. So it's a conjugate of the original subgroup. And that happens in any transitive action. More generally, if G acts transitively on S, and G sub S, and you want to compare, and G sub S prime, so say G of S is equal to some S prime. So we find 2 points in S, and we find a G that takes us from S to S prime. And we want to know what the stabilizer of S prime is in terms of the stabilizer of S. It is the conjugate GS, G inverse inside of G. So that the stabilizers are conjugate. So again, this is a triviality if you work it out, but just see it. So suppose I have something that stabilizes S. So here's an element in GS. And I want to see that an element of this form stabilizes S prime. Well, G inverse takes S prime to S. Then I have an element that stabilizes S. Then I go back to S prime by G. So it's clear that this is contained in the stabilizer of S prime. Then you have to show that something of S prime, when you conjugate it, gets the stabilizer of S, which is the same argument backwards. In fact, this is really no more general than the previous. And this is a surprising thing I want you to take out of this lecture. So we have this very general notion of a G action on a set. And when we have a G action on a set, it breaks the set up into orbits, OS, OT, OU, etc. And on each one of these orbits, we have a transitive action. So if you want to break up any action, it's broken into a bunch of transitive actions. So the key is to understand what a transitive action looks like. Now here's an example of a transitive action on this cosets of the subgroup. And the reason that this result is no more general than this result is that any transitive action is isomorphic to the action on the cosets of the subgroup. Because if G acts transitively on S, and S in S has stabilizer G sub S, then there is a bijection of G sets, so sets with a G action, the things that we're looking at now, between S and the cosets of GS. G mod GS is bijectively identified with S. That takes an element here, and it maps it to the element G of S. Now you see that that only depends on its coset mod GS, because if I modify G by multiplying on the right by something that fixes S, this element is still well determined. Right? First I apply an element that fixes S, I stay at S, and then I apply G. So this is well defined. As only depends on coset, GGS. You get every element in S this way. It's a surjective map because the action is transitive. So if I want to get to some S prime, I find some G and G that takes S to S prime. It's a transitive action. So it's surjective. Now the only things that fix, and it's also injective. The things that take a coset. Yeah, the inverse image of each point here is exactly a coset. And then if you use the left action of G on this set by left multiplication and the normal action of G on S, they're converted to each other. So that we can identify all transitive actions with this kind of action. A transitive action determines a subgroup, the stabilizer of a point. And once you know that subgroup, the action on the cosets is the same as the action on the set. It really doesn't determine a subgroup, though, if you think about it, because to get this G sub S, we have to pick a point in the set. Right? If we chose a different point in the set to define its stabilizer, we'd get a conjugate subgroup. So that's the real moral of transitive actions. A transitive action is exactly the same as a conjugacy class of subgroups. GS and G. And so, every time we have an action of G on a set, we break it into orbits, and to each orbit we get a conjugacy class of subgroups such that the orbit is identified with the action on cosets. Now, so far we haven't had too many interesting actions, but we're going to get a ton of interesting actions coming up. If, by the way, G is a finite group and S is a finite set, then we know if G and S are finite, then we can conclude from this that the order of G is the order of S times the order of the stabilizer group. Because the number of elements in this set is the same as the elements in S, and we've already proved that for any subgroup, its order times its index is the order of G. So we get a little counting formula. And we're going to use counting formulas like this for all kinds of interesting G actions. So, as I say, this left translation is a stupid action, but we could have G act on itself as an example of an interesting action where we're going to do all kinds of counting formulas. G acts on S equal G by conjugation. Namely, S goes to GS G inverse. Here the orbits are the conjugacy classes. And we're going to want to count, and G sub S is the centralizer of S. And S is equal to the elements in the group such that GS is SG. So we're going to count conjugacy classes and elements in the conjugacy class by calculating what their centralizers are, etc. And we'll be using this kind of orbit formula throughout. The rest of the talk, the rest of the stuff on group theory, we're going to leave Euclidean motions. We're going to go into the abstract theory of finite groups, counting conjugacy classes, what are called the Celoff theorems, predicting the existence of subgroups of certain order. And that should take us another 2 weeks of group theory before we go into rings. Okay? I didn't go into the complete wallpaper designs. As I say, this is a fascinating subject. It's of enormous interest to chemists, not just in 2 space, but in 3 space. Because if you can imagine the same problem in 3 space, where you look for lattices under the orthogonal group of dimension 3, up to translation by things, that might be in the forms of crystallization in atoms or in molecules, and the chemists have made a complete classification of the discrete subgroups of the motion groups in free space. And that allows them to predict how various things will form. I will do some things about the fact that we may want to classify the discrete subgroups of SO3, like we did for SO2, they were all cyclic. For SO3, you get some very interesting discrete groups. In particular, A5, the alternating group on 5 letters, turns out to be a discrete subgroup of SO3. And that's the group that's recently been promoted as the model for the universe, which I think we ought to be all cool up about. So I think I will tell you about A5 being a discrete subgroup of SO3 and how you get the model for the universe that's just been proposed, even though I believe it's false.